Okay, so we'll start with the air compressors. Okay, so exactly is a compressor? We have already discussed. So, what is a compressor? Can anyone tell what we do in a compressor? Hello.
It is a device to pressurize the gaseous medium.
No, no. Actually, what we do in a compressor, we generally compress the gases from a low pressure to high pressure. So that is the main function of the uh, compressor. So the we'll write. So what do you want? In this class, should we discuss the more focus on the numerical part, or you want me to start from the beginning and end it? Because
Sir,
hello,
from beginning to end, sir.
beginning to end, because
Yes, sir.
it will take a time. So if you want, we can skip some part in between. We will focus more on the topics which are relevant point of gate, because in gate there are not many questions which has been asked from this topic. So based on
Yes, sir.
Okay, sir.
instead of, I think, doing all the part, I think we should more focus on the numerical part, because that is the part from which there are many questions has been asked in the gate exam. Okay.
ओके सर सर
Okay, sir.
आप बस हेलो
Yeah, yeah.
सर टाइप्स ऑफ कंप्रेसर थोड़ा डिस्कस कर लीजिएगा 2 मिनट सर
Okay, okay. So what is a compressor actually? Can I have already told you that. We'll start. What is the topic? Compressors. Okay. So what is the function of a compressor? With the help of a compressor, uh, we are mm, we are increasing the pressure of the gas or working fluid, you can say. Okay, with the help of a compressor we are compressing it. Because of the compression, the pressure of the suppose the pressure initial is P1, so it will increase to P2. Okay, on PV diagram you can see the process like this. Okay, 1 2, pressure of 2 is higher than 1. Okay, so classification, uh, classification of compressors. I also want to tell you that this is the last class before the gate exam, because the last date for that this by NPTL it is 31 January. So we are having the session on Wednesday, so it will come on 1 or 2 Feb. So this is the last class. So we will not be having any class from the next week. Okay.
ओके सर
Okay. So we'll discuss the classification of the compressor. So compressor are basically classified on the basis of operation, on the basis of pressure developed, and on the basis of the volume handled. There are all and fourth category is the on the basis of the pressure rise. Okay. So base classification are done first. A, on the basis of principle of operation, but this we are discussing itself, but this is in relevant in relevant for the gate point of view, but I'm telling you we will only discuss in a glance only this topic. Okay. Second, on the basis of pressure develop C on the basis of volume handled and D on the basis of pressure rise. Okay, so we'll discuss one by one. First, on the basis of principle of operation. On the principle of operation, there are basically two types of compressor. First one is the displacement compressor, positive displacement compressor, positive displacement pumps or compressor, you can say, both are same term. Okay, and second one is the rotary compressor. Okay, so what do you want? Do you want only the classification, or do you want me to explain this further also?
सर the pressure rises maximum मतलब comparative analysis थोड़ा सा बस.
Okay, so in first one in a positive, the example for positive displacement compressors is the reciprocating compressors. Its example is reciprocating compressor, like the this one. Uh,
Cylinder piston
yeah,
arrangement, right?
piston cylinder only, that was I piston cylinder assembly, piston cylinder assembly type. Okay, it is a example of positive displacement. So what exactly happens in this type of compressor? The pressure rise which we see in this type of compressor, pressure rise is occurring because of the decrease in volume of the confined cylinder. So what exactly happens? Suppose there is a gas here. I'll show you in next page. Suppose there is some amount of gas. Suppose it is in a there are basically two dead centers. I'll show you. That is the top dead center. This is the bottom dead center. Okay. So suppose there is some gas confined. The volume here, it is known as clearance volume. Okay, and the this volume is known as the swept volume. Okay, so suppose there is some amount of gas here. So initial condition. So when we compress it, so what happens? This gas is its volume tends to decrease. Suppose it is a bottom dead center. Okay, so these gases tends to volume tends to decrease, and because of this volume decrease, this is the top dead center. Because of this, there is a mm, rise in pressure. Okay, rise in pressure due to volume change in the compressor, or in the, you can say that piston cylinder assembly. Second type of compressor is a rotary compressor. So what exactly happened this type of compressor? Secondary, can anyone tell? rotary compressor, because you are getting a big hint from the name itself.
Kinetic energy is transferred to pressure energy of the working fluid.
Yeah, you are right. So what exactly happens in this compressor? Exactly happens? We first impart high kinetic energy to the working fluid, okay, by the means of any rotary element, okay, called as what we call that rotary element, impeller.
Impeller.
Yeah, impeller, okay.
Sir, what
So
is runner then?
yeah,
What is runner?
you can call it as runner also. It is any rotary element. I am calling it as impeller. You can also call it as a runner also, okay.
Okay.
It is only a rotary element. That's why I haven't written by the means of any impeller, or that's why I have mentioned a rotary element. Okay,
Okay.
and that kinetic energy is then used to increase the pressure of the gas or working fluid in the diffuser. Diffuser, we have already know that diffuser, what exactly happens like this. It is a high kinetic energy V1 comes and pressure P1, and it exits as a low velocity V2 and high pressure P2. Okay, examples for the rotary compressor are, can anyone tell? First one is the centrifugal compressors, in which centrifugal force is used. Second one is the axial flow compressors. In this also, the by a rotating element, we first provide the kinetic energy, and then pressure rise takes place. Okay. Second mode is B is on the basis of the pressure developed. On the basis of the pressure developed, it is of three types. First one is the low pressure. Second one is the high pressure, medium pressure, and third one is the high pressure. If the pressure is less than 10 bars, then it is known as low pressure compressor. If the pressure is greater than 10 bar and less than 80 bar, so it is, if it is in the range of 10 to 80, it is known as medium, and if it is greater than 80 bars, then it is known as the high pressure compressor. Okay. Third is the see basis of on the basis of the volume handled by compressor. Okay, so on this basis also, it is of three types. First one is the small handling capacity compressor. Second one is the medium capacity. Third is the large handling capacity. So if the volume handled by the compressor is less than 9 millimeter cube per minute, then it is known as a small volume handling compressor. If the volume handled by the compressor is between 9 to 3000 millimeter cube per minute, then it is known as medium handling capacity compressor. If it is greater than 3000 millimeter cube per minute, then it is known as,
Sir, it is millimeter cube or meter cube?
oh, meter cube per minute. Okay. And fourthly, D, on the basis of pressure rise. Okay, on the basis of pressure rise, uh, these compressor are classified as first one fan, second blower, and third one compressor. Okay, so in a fan, what is the pressure ratio rise?
Very
It,
less.
yeah,
One
very less.
point
1.1, it is less than 1.1. And for blower, how much it is?
two. सर तुक्का मार रहा था.
Yeah, 1.1 to 2.3. And for compressor, it is very high, greater than 2.3. Okay, hello.
Okay, sir.
Okay, so we'll discuss reciprocating compressor because it is very important for the gate point of view. Reciprocating compressor is a positive displacement type of compressor. Okay, in which, because of volume change, pressure rise takes place. Okay, so we will what are the drawbacks, what can be the drawbacks of the reciprocating compressor?
Pulsating.
First we will discuss, I will tell some more point about the reciprocating compressor. Okay, so then we will discuss about the drawbacks. Okay, so what exactly happens in a reciprocating compressor, we have also already discussed it. Because of the volume change, pressure rise takes place. So how much, what is the pressure which can be developed by the reciprocating compressor? So pressure greater than 1000 bar, that is very high pressure, high pressures can be generated via reciprocating compressors. Okay, say what are the main parts of the reciprocating compressor? As we have already discussed, it is work on a piston cylinder type of arrangement. Okay, so this is top dead center, this is bottom dead center, this is the uh, that clearance volume, this is the swept volume, and total volume is equals to the total volume Vc plus Vs. Okay, so uh, basically what happens in a reciprocating compressor, there are mainly two valves are there. One is the suction valve, suction valve. Second one is the discharge valve or discharge. Two processes are there: suction, compression, expansion. Okay, so compressor consists of three processes. First one is suction of the working fluid. Second one is the compression of the working fluid. Third one is the discharge of the working fluid. Okay, So what can be the drawbacks? You
Volumetric efficiency decrease.
drawbacks that we will discuss later when we will discover volumetric.
More vibration.
No, first one is the handling capacity. Handling capacity is less because the uh, piston cylinder arrangement, the capacity of the piston in cylinder is confined. So capacity we have to decide on the basis of the piston and cylinder assembly only. So handling capacity is the drawback, first drawback. Second drawback is the hello. This yeah, there is no any other drawbacks. The biggest drawbacks is the handling capacity only. We can handle only small amount of that working fluid, that is in the range of 5 to 8 millimeter cube per minute, which comes in the range of small handling capacity. Okay, small handling capacity plants. Okay, so this is the drawback. So we will discuss about the work input expression for this uh, compressor, reciprocating compressor. Okay, with clearance volume and without clearance volume. So we'll discuss first case one with clearance volume, work output of compressor. Okay, so if there would not be any that clearance volume, how would the process look like? Suppose this is a piston cylinder arrangement. This is the top dead center. Okay, the bottom dead center then touch directly to the bottom itself. Okay, bottom dead center, this is top dead center. So because there is no clearance volume like the one here it is shown in this figure, so the piston cylinder arrangement will directly touch the top, okay, or bottom you can say that, because of which problem may arise. So
Sir,
yeah,
I want to ask a thing, sir. Sir,
yeah,
this 5 to 8 meter cube per minute is the exit volume or the uh, exit discharge or the inlet discharge?
it is the
Sorry, inlet of the
it is the total handling capacity, like this the space we are talking about, this one.
VC plus VS.
Yeah,
Okay, only
yeah,
VS.
yeah. Okay,
Okay.
so total amount of volume which can be handled at a time. Okay, that we are talking about. So we are basically talking about this one, the this VC plus VS itself. Okay, so
Okay.
in case one we are deriving the network output of the compressor without clearance volume. So if there will be no clearance volume, then how would the process look like in the uh, first PV diagram? First, what will happen in this process? First, suction of the air takes place from suction of the air takes place from 0 to 1. Okay, so suction of the air 0 to 1. Wait, I will first draw and then I'll explain. 0, 1, 2, 3. So 0 to 1 process was suction of air takes place at constant pressure. Then from 1 to 2, compression of air takes place at um, via that this compression works on PV to the power n, that is polytropic, or you can say that polytropic cycle, or that isentropic. So here value of n is not known. So it is a compressor basically works on here we are not talking about the ideal compressor. Ideal compressor basically works on isentropic process. So in actual the compression doesn't works on the on that what we said isentropic process. It works on poly in between the from that isothermal and that isothermal and isentropic process. Yeah. Wait, I'll do it. This is 1, this is n, this is gamma. So compressor works in this range. This is a isothermal process. Okay. This is a isentropic process. And in between this range, the your compressor works. Actual compressor. Ideally, we think that a compressor work in that gas turbine cycle. We were assuming the ideal compressor. So ideal compressor work on isentropic processes only. Okay. So if the value of n, that value of n, it is given 1.4, or they have given that the working fluid is, yeah,
N lies between 1 to gamma or 0 to gamma.
it lies between n 1 to gamma, I think so. That I that we have that 1 to gamma, that we have to see. Actually, I don't remember that because I have and,
सर 1 to गामा ही करेगा क्योंकि वर्क इनपुट में अपॉन n-1 होता है ना,
yeah.
तो 1 से तो बड़ा ही होना चाहिए.
Okay. So it lies between 1 to gamma, but actually, in most of the cases in reciprocating compressor, generally the working fluid is a that we are talking about. Working fluid is a gas or air. Generally, we take air only. So for air, Cp and Cv are constant. That is, Cp is 1.005 kilojoule per kg Kelvin, and Cv is 0.718 kilojoule per kg Kelvin. So because Cp and Cv for air are constant, so what exactly happen? The value of gamma n comes out to be 4. So therefore, we we, that so that compressor we work uh, because n comes equals to 1.4, so it is equals to gamma is also 1.4. Therefore the compressor, we assume, that works on isentropic process. In the in that gas turbine we were talking about, the working fluid was there only. That's why the we were assuming that the compressor work on that what compressor work on isentropic process. Okay. So what will be the because first in this process, the first 0 to 1 process, what exactly happens? Suction of the air takes place at constant pressure, and from 1 to 2 compression takes place. Okay. And from 2 to 3 discharge of air takes place at constant pressure. Okay. So what exactly happens? So the network output. So what will be the network output come? So network output for whole the process, what it will be the? So network output will be the work done during suction plus work done during by the compressor during by compression plus work done during discharge. Okay, so we will individually calculate these three, and then write the we will write the network output. So what will be the work done during the section, because it is a constant pressure condition. 0 to 1 suction of air takes place at constant pressure P. Here the pressure is P naught is equals to P1, and here it is P2 is equals to P3. Okay. So what will be the work done? You have already studied that thermodynamics part. For a constant pressure condition, what is how we write the work done?
P naught V1.
Delta V.
Delta V. Yeah,
Delta V.
yeah. So work done during the constant pressure during the section will be given by P naught. Okay, P naught
V1.
or P naught or P1 we will take as P only. So P naught or P directly we will write P only, lower pressure P. So no, no, P1 we will P naught or P1, anything we can write. P1 into what will be the
V1 V naught.
initial volume minus final volume. So what is the initial volume? Initial volume is 0 from the diagram. So we'll write 0. Final volume will be V1. So how we'll write? Minus P1 V1. Okay. So work done during the compressor. What will be the work done during the compressor? Since compressor it is working on the polytropic condition. So P1 V1 minus,
P2
yeah, we will write higher pressure, we write first P2 V2 minus P1 V1 upon n minus
N
1.
minus
Okay, and from this is 0 to 1, then from 1 to 2 compressor, then from 2 to 3 again it is discharge. So work done during discharge is given by, it is again a constant pressure condition. So here the pressure will be P2, P2 or P3 is same pressure, and volume will be initial volume minus final volume. Initial volume is V2 and final volume is V3, which is 0. So it will come out to be P2 V2. Okay. So then we will write the net work. What will be the net work? It is the addition of the all three works, that is the suction work plus compressor work plus discharge work. Okay. So suction work is P1 V1 plus,
Sir,
yeah,
sir, will it not be considered as an open system?
yeah, it will be considered as a open system.
So
So
the work compressor will be n by n minus 1, na, sir?
yeah, that's what I'm will that will come. Wait, I'll tell you how it will come. Okay, just wait.
Okay.
Here n minus 1. Okay, and here here it is negative sign. Here it will come P2 V2. Okay, now we'll rearrange this. So P2 V2 minus P1 V1 will bring these two terms one side, plus P2 V2 minus P1 V1 upon n minus 1. Okay, so now we will take P2 V2 minus P1 V1 common. So 1 plus 1 upon n minus 1. So P2 V2 minus P1 V1 into n minus 1 plus 1 upon n minus 1. So it will come n upon n minus 1. This only you were talking about, na? The for network done. So since compressor work you might have already studied in that thermodynamics that for an open cycle, work done for an open cycle is n times the work done for then uh, n times the work done for a closed cycle. Have you studied that part? Yes,
Yes,
you
sir.
might have taught. So
Yeah.
compressor, since compressor is working on a closed cycle and closed cycle, so the work, so it is directly coming that n into work done by the compressor. We can directly write. Okay, so n
Sir,
into, yeah,
can we go to previous slide?
yeah,
Sir, here work done in 0 to 1
yeah.
means we take final volume minus initial volume.
Final initial. We take initial only, I think. That you can check actually. It doesn't matter if it will come negative also na, then in the final answer which we generally comes, so we have to take that modulus.
Okay, sir.
Okay, so it that is not a problem. Okay, so we were here only for an open cycle. The work done is n times the work done for the closed cycle. Okay, so compressor generally works on an open cycle. So for an closed cycle, the work done is given by this one only directly, P2 V2 minus P1 V1 divided by n minus 1. So directly also we can write the here also compressor from, that is a closed cycle. Okay, but for you I have done this part. You can directly write from here also. So we can
It is only when the clearance volume is zero. Only when, in
yeah,
this case.
yeah, when clear, I have already stated here when the clearance volume is 0. Okay, so we'll rearrange this form, work done form. So what will be the work done? So net work done will be P2 V2 minus P1 V1 into n upon n minus 1. Okay, so we will take out, wait, I have written wrong. We should write n minus 1 first here, then P2 V2 P1 V1. So we will take out P1 V1 common, P1 V1 to n into n minus 1. So what will come? P2 V2 upon P1 V1 upon 1. Can I write like this? This network done. We have just taken out P1 V1 common. Hello.
Yes, sir. It can be written.
Okay. So now we already know that for polytropic cycle, PV to the power n equals to C, or we already know that. So P1 V1 to the power n, P2 V to the power n. If we'll take out, then what will it will come? V2 upon V1 to the power n is equals to P1 upon P2. Okay, so V2 upon V1 will come P1 upon P2 to the power 1 upon n. Okay, so if we will put this value, suppose we are taking this as equation 1 and this as equation 2. So if we put 2 in 1, what we will get? P1 V1 n into n minus 1, that is network bracket. What we will get?
RP to
P2
the power
P2 upon P1 and
into P1 upon P2 to the power 1 by n.
P2 by P1 or
uh, what what we will
This,
get?
this to the power 1 minus 1 by n.
Yeah, this to the power 1 minus 1 upon n. This we will get minus 1 And from here, what we can write further?
P2
N,
by P1 is
n minus 1, P1, V1. This P1 upon P2, n minus 1 upon n minus 1. Okay. This is the work done. Work done without clearance volume. Okay. So what will be the unit for this?
joule, kilojoule.
Yeah, joule, right. Joule will be the unit. Okay. So second case two, if there will be clearance volume, so how will the work output expression will look like with clearance volume? The process, the diagram is like this only. In previous case, we were ignoring this clearance volume. So now clearance volume will also come. Okay, this is the clearance volume. This is the VS, top dead center, bottom dead center. Okay, so the diagram now will look like this: 1, 2, 3, 4. Okay, the process will be same. This will be polytropic compression. This is expansion. This is you can say that heat discharge will take from 2 to 3, and from 1 to 4 suction will take place. Okay, so
Sir,
yeah,
the
hello,
work formula we have derived above
yeah,
means we have done that because we don't know V2.
V2, no, VC we don't know that clearance volume we have neglected in this case. We have directly considered that clearance volume is there is no clearance volume is zero. VC is zero here. That piston which directly touch the top. We are assuming that. Hello.
Yes, sir. Means
Means
work compressor is equal to n times of work closed.
yeah, that is a general that you can also neglect that I'm talking about the that compressor is working on a open cycle. So for an open cycle, that is a general you have already discussed in the thermodynamics that for an open cycle, work done for open cycle is n times the work done for an closed cycle. Closed cycle, that is a general term that is valid to all the that gases or working fluids. Okay, which generally works on air and or gases.
No, sir. Means I'm just asking here the second box is there.
Yeah,
So this formula means I am clear, but why we are modifying this formula?
which formula? This
We cannot
no,
measure exactly.
no, this is you are saying this formula, na? This formula we are modifying here.
Not that.
Then which formula?
Ah, yes, it is same only.
Yeah, it is same only. Just we have rearranged the terms. It is not different actually. This formula you are saying, na? This one and this formula and this formula.
Yes, sir. Yes,
Both are same actually. You can see.
and this formula we are just modifying.
Yes, we are just modifying that in terms of pressure ratio and that.
Okay, sir.
Okay.
Sir,
So yeah,
but if we want to use that formula without modifying, then in place of V2, what we will put?
V2 here you can calculate na. The conditions will be given actually in numericals. In while derivation, we have to take variables only v1, v2, and this. But in numerical, when they will give, so they will give enough data that you can easily calculate. Okay,
Okay, sir.
so this is the volume v1, v4, v3, v2. Okay, so here v3 is the lowest volume till the from top bottom dead center. So V3 is itself the compression volume remained at the end of the compression. The V3 is equals to here volume of compression is equals to V3 only.
Okay, sir.
Okay, because we are compressing it, then we are discharging it. So top dead center there is some space left, and that is known as the clearance volume, and that is equals to V3 only. Okay, so what here in case 2, since we are considering the uh, clearance volume, so what will be the network output in this case will look like? Hello,
Yes, sir.
how will it look like? Okay, I'll tell you then. It will be equal to work done from 1 to 2 minus work done from 3 to 4. So 1 to 2 is a compression process, 3 to 4 is a expansion process. Okay, so from 1 to 2 we have already know that we will consider the area. Okay, P V. So we will consider the area directly from here to here directly, and then we'll minus it from the area. So we will get this area which we want. Okay, this is 1 2, this is 3 4. Okay, so from 1 to 2 we already know from previous case 0 1 2 3. Okay, what we know that work done from 1 to 2 for compressor is given by n into n minus 1 into p2 v2 minus p1 v1. Okay, or we can also write like this into n minus 1 p1 v1 into p2 upon p1 to the power n minus 1 upon n minus 1. Okay, this we can write. So this is the total work from 1 to 2. So we are taking total area here, this one, and when we will minus this area total from this area, so we will get this remaining area na 1 2 3 4. So from here we area for this 0 4 0 4 3 2, what we will get this work done from 3 to 4, since it is also but it is an expansion process. So we can also we can write same here n into n minus 1 into
P4 V4.
yeah p4 v4 minus
सर सिंपली बाहर ही ले लेते हैं ब्रैकेट.
no, here we have to take p3 v3 higher pressure we write first, then the lower pressure p4 v4, same, because here we were taking higher pressure p2 v2 higher, minus P1 V1 lower. So here also we have to take the fluid which is at higher fluid, higher pressure first, and then the lower. Okay, so we'll write P3 V3 minus P4 V4. So work done 3 to 4 will come, n into n minus 1 into P3 V3 minus P4 V4. So this we can again rearrange because 3 to 4 is a polytropic process. Okay, so P3 V3 to the power n, P4 V4 to the power n. So from here what we will get, V3 upon V4 is equals to P3 upon P4 to the power 1 upon n. So when we will rearrange this one, n into n minus 1, so when we will take out P4 V4 common, so it will come P3 V3 upon P4 V4 minus 1. So when we will put this value here, so what we will get, n into n minus 1 P4 V4. Okay, so we'll get P3 P4 into 1 minus 1 upon n minus 1. So n upon n minus 1 P4 P4 V4 into P3 upon P4 to the power n minus 1 upon n minus 1. Okay, so net that from 3 to 4 we will get n into n minus 1 P4 V4 into P3 P4 n minus 1 upon n minus 1. Okay, so the net work output for this cycle will come out to be work done from 1 to 2 minus 3 to 4. So from 1 to 2 we already know that n into n minus 1 and P1 V1 into P2 upon P1 to the power n minus 1 upon n minus 1 minus n into n minus 1 P4 V4 P2 upon that is P3 upon P4 to the power n minus 1 upon n minus 1. Okay, so we already know that pressure P3 is equals to P2 and P4 is equals to P1. So this term will also become equal to this term only, P3, because from here diagram we can see that P3 P2, this P2 and P3 and P1 and P4 are same. So from here what we can rearrange this term as network output as n minus 1 we can take as directly. I am taking common, so P1 V1 into P2 upon P1 to the power n minus 1 upon n minus 1 minus P4 V4, because P3 is equals to P2, so directly I am replacing it, and P4 is equals to P1, here also I am replacing n minus 1
Also,
upon
sir.
n minus 1. Hello,
Also, sir, P4 V4 वाले में P4 को
yeah,
P1 लिख सकते हैं.
yeah, here also we can write P1 only. So n into n minus 1. So pressure P1 we can write common. So V1 minus V4, and this P2 upon P1 to the power n minus 1 upon n minus 1. This we can take in bracket. So the network output will come like this. So this V1 by V4 we can write it V actual. That is the actual volume which is entering into this confined area, that is between the top and bottom dead center. That is the actual volume of air, actual volume of working fluid which is sucked. Okay, so finally we can write the expression as network output is equals to n into n minus 1 P into V1 actual we can write, or V actual directly you write V actual into P2 upon P1 n minus 1 upon n minus 1. Okay. Hello.
Yes, sir.
Yes. For this V actual will be volume of the stroke.
V actual is the actual
Swept
volume.
volume.
Volume of the stroke.
Yeah, actual volume of the air sucked.
सर एक्चुअल वॉल्यूम तो V1 है ना.
V1 minus V4. It is the actual volume which is being sucked from process 4 to 1. Na? It is a suction process 4 to 1. This is a suction process. This is discharge.
Yes, yes. Okay, sir.
This is compression. This is expansion.
So means it is not swept volume.
Yeah. Hello.
Means is it swept volume or
No, no,
It is
sir.
less than
No, no.
volume.
Cert volume is not that. Cert volume is actually total volume. Swept volume is between. Yeah, you can also say that it is a swept volume. Yeah,
Swept volume तो V1 minus V3 है सर.
swept volume.
Swept
Yeah,
volume
yeah, yeah, yeah. Swept volume is total volume. Yeah, swept volume.
V3.
Swept volume is actually the total volume we call as total volume. So total volume is Vc plus Vs, and Vs is this V1 minus V4. Okay.
नहीं नहीं सर.
Swept volume.
सर swept
No,
volume
no.
तो
So
V1.
yes, sorry. Total I have written wrong. Total volume is equals to the that clearance volume. Clearance volume
Plus
plus swept volume. So it is equals to total volume is equals to Vc plus Vs. Okay. This Vc is equals to V3, and that Vs is equals to V1 minus V4. Okay.
yes
And
sir.
नहीं सर VS हो जाएगा V1 minus V3 सर.
Yes sir V3.
Vs V1 minus
V3 सर वो जो डायग्राम बनाया है उसमें चेक कर सकते हैं.
V swept volume. Yeah. Right. It is V1 minus V3. Okay. So now we will discuss the volumetric efficiency now. What is volumetric efficiency?
V1 minus V4 upon V1 minus V3.
Yeah, it is defined as the ratio
At
ratio of the actual volume at the entry of compressor to the total swept volume. Okay, so what is the actual volume? V1 minus V4, and what is the swept volume? V1 minus V3. Okay, so it is given by this. So if we will rearrange this in that term, should I derive or should I directly tell the formula? Hello.
no need of derivation, sir.
Okay, so I am directly telling you the formula then. So
Sir, what is the name of the process 3 to 4?
3 to 4 is 1, 2, 3 expansion process.
Sir, where is this expansion taking place? Inside the cylinder.
Yeah, inside the cylinder itself, because
गैस
clearance
गैस
volume. Yeah,
डिस्चार्ज. सर गैस तो डिस्चार्ज कर दिया तो एक्सपेंड क्या हो रहा है?
some amount of air is left na, that will again takes expansion of that some amount of gas is there, clearance volume, so that again gas expands, so that we are taking into consideration,
ओके.
because some amount of gas is left na.
Yes, sir.
So,
Yes, sir. Okay.
so what is the volumetric efficiency? It is the V1 minus V4 upon V1 minus V3. So if we will rearrange, I'm not doing the derivation, I'm directly telling you the formula. If you will rearrange this in terms of that volume from the processes, so you will get the formula 1 plus C minus
Minus
C
RP to the power 1 by n.
V, yeah, directly I'm writing P higher upon P lower to the power 1 upon n, whereas C is the compression ratio, okay, which is given by Vc upon Vs, okay.
Sir, compression or clearance ratio?
Yeah, clearance volume upon that swept volume, that C, we normally call it compression ratio only, we call it, okay. So I'm directly written this formula because derivation will kill the time, and we are already short of time because it is 7:23. So we are roughly all we'll having 1 hour more. So we have to do problems also. So that's why I'm that removing that part, derivation part. Okay. So
Okay, sir. No issue, sir.
because you can understand. So what will be the pressure ratio? Pressure ratio for volumetric efficiency if it will be equals to 0. This question may can come anytime. Till now, till they haven't asked, but they can ask uh, this question. So what will be the pressure ratio? Can anyone tell? If we put 0 here, so 1 plus C minus C, P higher upon P lower to the power 1 upon n. Okay, so if we will write here 0 and
Equals.
yeah,
Both are equal.
what
Both pressure ratio equal to 1.
what your sound is, I'm not getting what are you trying to say. Hello.
Volumetric efficiency is 0%. It means the pressures are equal. Higher pressure and lower pressure.
That what they can ask the what will be the pressure ratio. Suppose we are working on a single stage compressor, okay, single stage compressor. So we'll compress it from 1 to 2, okay. So we can write 0 is equals to 1 plus C minus C into P2 upon P1 to the power 1 upon n. So if we will take C common, so P2 upon P1 to the power 1 upon n minus 1, we can write like this, and C will go that side, C into P2 upon P1 to the power 1 upon n minus 1 is equals to 1. So P2 upon P1 to the power 1 upon n minus 1 is equals to 1 upon C. So further we will P2 upon P1 to the power 1 upon n minus 1 is equals to 1 upon C. So P2 upon P1 to the power 1 upon n is equals to 1 upon 1 plus C. So P2 upon P1 will come as 1 plus 1 upon C to the power n. Okay, so this question may come because till date they haven't asked. They have only asked 2 or 3 questions on this this part. So they haven't covered too many. They have mostly asked the question on gas turbine and this only. Second one, Rankine cycle. So if they will ask question, they may ask from this part also. Suppose that if a reciprocating compressor is working and if the volumetric efficiency is zero, then what will be the pressure ratio for a single stage or two stage, any stage they may ask. Because compressor normally works on a doesn't work on a single stage. They work on more than one stage because uh, if we are compressing the air to a very high pressure in a single stage compressor, then the temperature rise in temperature will also increase beyond a particular range, which may damage the piston and cylinder assembly. So for the and that may result in the leakage because the temperature, if we are increasing in one stage, then the pressure will be so high that temperature will rise will also be very high, because of which leakage may occur in the piston cylinder arrangement. So therefore, if we want to increase the pressure to a very high extent, then we generally employ multi-staging. We compress the air in more than one stages. Okay, that's
So
yeah.
volumetric efficiency zero means that it is a closed system.
Volumetric efficiency zero. Volumetric efficiency zero. I don't get what are you trying to say.
Sir, since no volume is being sucked inside the system, so it has become a closed system.
I don't know actually this answer.
Okay, sir. Okay.
Okay. So we are talking about the multi-staging. Why do we need multi-staging? Multi-staging. Why we need multi-staging? Multi-staging of compressor. Because if we compress the air or working fluid in a single go or in a single stage, then the temperature rise will be very high. Temperature rise will be very high, because of which leakage, damage slash leakage in the piston cylinder assembly may takes place. So what we actually, for eliminating this, we are increasing the pressure. If we want to increase the pressure, so we are increasing pressure in stages. First we increase from 1 to 10, from 10 to 50, like this. We are not increasing. Suppose we want to increase from 1 to 250, so we are not directly compressing it to from 1 to 250. We are first increasing up to 10, then from 10 to 40, 40 to 100, like this we are compressing. Okay, because it will reduce leakage problem. Multi-staging, that's why we are doing multi-staging.
But sir, in RSC we have studied that the work input to the compressor is directly proportional to the inlet temperature to it. The
I,
inlet temperature of the fluid.
but RAC is different, and this compression part is different, because in RAC we are using different working fluid. Here we are taking as a working fluid as a air.
Okay, sir. Okay.
So working fluid plays a very important role in different application. Okay.
Okay.
So that's why this question also they may ask in one question, why we are using multi-staging. 1 mark they can ask, why multi-staging is necessary. Okay. So now we will go to intercooler. Then from there we will start the numerical. Okay. I have also prepared some questions on the array standard cycle because someone of you was saying that to cover that topic also. Hello. But
Sir, in this, only the dual cycle part is the important.
dual cycle, not auto and diesel cycle is more important in a standard cycle for gate point of view. I am saying
Okay, sir.
because from last 2 or 3 years, every time they are asking a question on auto cycle or a diesel cycle.
Okay, sir.
Okay, sir.
So you should do that part. Okay. So we will now discuss the use of the intercooler in a during multi-staging because the temperature rise is very high. Okay. So uh, in multi-staging we are using intercooler. Use of intercooler in multi-stage compression. So with the help of intercooler, what exactly happens? Uh, the temperature rise is decreased because of which leakage problem can be eliminated. Okay. In piston cylinder can be reduced. So as we have already discussed intercooler in gas turbine. So how how does we represent it on a TS diagram? Can anyone tell? With the help of intercooler, what exactly happens? We have already discussed in gas turbine.
We cool the compressed air.
Yeah. So what exactly happens? So in by using intercooler, work input, work input, work input to compressor decreases. We were in gas turbine. We wanted to decrease this part, na work but here in case of compressors while we are compressing our main task is to decrease the temperature in order to eliminate the uh, in order to prevent the damage to the piston cylinder arrangement. That's why even though it is reducing the compressor work, we are using intercooler because our main task is to prevent the damage for the piston cylinder arrangement. Okay. So even though if we will
Sir,
get less work output,
work
then
reduction is sir, work reduction is beneficial now because compressor need work. So work input is
yeah,
less. So it is beneficial, sir.
yeah, wait, actually one call is coming. Hello, 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 hello. Am I audible
Yes,
now?
sir. Yes, sir.
Yeah. What were you telling?
Sir, since work input is reducing, it is beneficial because we have to provide less work to the compressor.
Yeah, I'm telling for gas turbine point of view. I was saying that by the use of intercooler in that in gas turbine, we were reducing the compressor work, and because of that the network output was improving. Network output was improving because output was the difference of the turbine work minus compressor work. So if the compressor work will decrease, so network output was improving. Okay. So but in
Yes.
case of in case of in case of But in case of compressors, in this, but in here, our main task is to here our task is to reduce damage of the piston cylinder leakage problem. It is occurring because of high temperature of the compressed air. So we are using intercooler in multi-staging, in between multi-stages. Okay. Hello.
Sir, due to using intercooling, pressure reduces or remains same.
Pressure will remain same, but temperature, the final temperature we are getting, it will reduce. Okay. Also because who was saying that in compressor we have to do work, so because of intercooling actually we are reducing the work input to the compressor, so there is actually a saving in work because of the intercooler. Wait, I'll show you how. Suppose we were compressing the air from 1 to 2 previously, 1 to 2 directly. Now we are using intercooler in between. So because of intercooler, what will happen? We are saving this much amount of work. Hello,
Yes,
hello.
sir.
So this much amount of work is actually saved. Saving of work due to intercooling. Okay. It is lower pressure, it is higher pressure, it is intermediate pressure, some intermediate. This is PV diagram. Okay. And on TE diagram, how we represent, suppose we are dealing with air. If we are dealing with air, then gamma comes out to be 1.4. So for that case, I am drawing. That is P lower, P intermediate, P higher. Okay. That is process 1, 2, 3, 4. That you can say that 2 dash. So here from we can dash 2 dash, here it will come 2, it will be 2. We can write it is 2 dash. From 1 to 2 dash, if we are directly compressing, we are getting this temperature. Okay. And if we are using an intercooler in between this, so final temperature we are getting this. So because of this, we can prevent the leakage problem. Okay. Hello.
Yes, sir.
Have you got that now?
Yes, sir.
Okay. Also because of that intercooler, we are saving the work which we are doing on the compressor. The person who was talking, he was saying right. Okay. So in that intercooler part, we have already discussed that the intermediate pressure, how it was coming. I am not discussing it again. So intermediate pressure will be the under root of the higher or and the lower pressure. Okay. It is again a derivation, but I am skipping it. How it will come, that I will tell you, that you can do at your home. So what
Okay. So the
work?
intermediate pressure is for less work input.
Yeah,
This intermediate pressure is for minimum work input, na?
minimum work input. Yeah, yeah, you are right. So work input from here you can directly from 1 to 2 and 3 to 4 you can first derive, and from that this will come in some pressure ratio form that I will write, that you can do directly. I am writing directly this n into n minus 1 p1 v1 into p2 upon p1. Derivation is actually not important for you for gate. but I'm doing for you n minus 1 p3 v3 p4 upon p3 into n minus 1 upon n minus 1. Okay, so it will 1. So if we are if we suppose we are using as a working fluid is air. Okay, so for air PV equal to MRT is valid. Okay, so if we can directly write from here P1 V1 is equal to MRT1. Okay, P3 V3 is equals to MRT3. That we are assuming that working fluid is a air assumption. Okay, so pressure P1 is equals to P2. P2 is equals to P3 is equals to P higher. This lower pressure P1 is lower pressure. P4 is the higher pressure, P higher. And if we are assuming perfect intercooling, so for perfect that cooling, temperature T1 and T3 will be same. These two temperature will be same. This we have already studied in the gas turbine cases. Okay, and T2 will be equals to T4I. Okay, so if we will put all these value in the equation 1, so what will be equals to, here also T2 is equals to T4 we can take, and so work input will come equals to M, suppose,
MRT1 into n by n1
yeah, n into
in
n minus 1. Okay,
MRT1
MRT1
into
for
P higher by to the power n minus 1 by 2n.
first will come P higher or P2.
P higher.
P2 is lower actually, I think so. P2, no, P2 is intermediate. So we will write P2, P
Sir,
intermediate upon P1 will
P2
be
or
P lower. Yeah, n
सर
minus 1.
फाइनली P है और n minus 1 by 2n कर सकते थे डायरेक्ट.
Yeah, we can write that also. But P higher upon P intermediate will come here. I'm writing in this from here actually. So now we can take all this as common term. MRT1 into n minus 1. Then all other things we can take from here. P intermediate upon P lower to the power n minus 1 upon n plus P higher upon P intermediate to the power n minus 1 upon n minus 2. Okay, so if we will this derivate equation 2 work input uh, for maximum or minimum, what we have to do, we have to derivate this work input with respect to intermediate pressure is equals to 0, and from here if we will that you can do at your home, we will get P intermediate is equals to under root of P higher into P lower. Okay, this question they may ask, that is for intercooling pressure for perfect intercooling. Okay, now again if there are multiple stages like this, you can say, Suppose first will compression start from 1 to 2, then intercooling. Okay, 1 2 3, again 4, again intercooling, again 5 6. Okay, if we are doing like this is P1, P2, P3, P4, P5, that is P6. Okay, so how we can write P2 upon P1?
P6 upon P1 to the power 1 by 5. एक second sir.
Yeah,
P6 by P1 to the power 1 by 5.
P2 upon P1. Suppose we are assuming perfect intercooling. So what will happen for perfect intercooling?
All these will be in GP.
Yeah, all the intermediate pressure will wait. Will write P2 upon P1. How will write P2 upon P1 first? It will be equal to P2 is a intermediate pressure. Okay, and P1 is a P lower pressure. It is P lower. It is a P higher pressure. Okay, so P intermediate pressure for a perfect intercooling, P higher upon P lower we can write, and it is P lower. So it will come out equals to P higher upon P lower. Okay, P2 upon P1. If we are assuming perfect intercooling at each stage, and from for uh, that 4 to 3, 3 to 4, how we can write P4 upon P3? For 1 to 2 we have written. We can how we can write?
Sir, can we go to previous slide once?
Yeah.
Okay, sir.
So what exactly assume? We assume that we assume uh, that for perfect intercooling, the pressure ratio at each stage is equal. Okay, so what we can from this we can get that P2 upon P1.
Equal to RP to the power 1 by 3.
Yeah, that will write P2 upon P4 upon P3 is equals to P6 upon P5. This we can write. For perfect intercooling, we assume that pressure ratio for at each stage is equal. Okay, so the overall pressure ratio we can write from here that it will be multiplication of this only, P2 upon P1 into P4 upon P3 into P6 upon P5. Okay, so as all three are equal, so the overall pressure ratio we can write P2 upon P1 to the power 3. Okay, so overall pressure ratio is equals to pressure ratio at each stage to the power number of
3.
stages. It is a general term. Here n will be the number of stages. Okay,
-2 होगा, n -1 होगा ना.
n
तो
minus 1.
+1 इसमें तो
No,
दो
no,
स्टेज थी ना
नहीं
सर. इन द
तीन.
previous we have only 2 stages.
No, we are having three stages. Na? See, from 1 to 2 we are compressing. This is the first stage. From 2 to 3
Yep.
second stage. From 5 to 6 third stage. So there are three stages actually. Okay, so it will be
Okay
equal
sir.
to where n will be n equal to number of stages. Okay, and this is valid for perfect intercooling. Okay, is it okay? Hello, it is also very important for objective.
Yes, sir.
Sir, can you turn up to the previous slide?
Yeah.
Okay, sir. Thank you.
Okay. Also, we have discussed in gas turbine that the compressor work should be equal if there are multiple stages we are compressing. So WC1 equal to WC2 equal to WC3. This we have to take, and the total compressor work we can write N into work done in each stage. Okay, because already all are same, so we can directly write the number of stage, and we can calculate for one stage and then multiply it by the number of stages, then we can get the total compressor work also. Okay, hello, this is valid
Yes, sir.
for perfect intercooling. Okay, T1 should be T3. Okay, and other temperature should also be same, that is T2 is equals to T4. Is it fine? And compressor work should be WC1 equal to WC2 if it is only one stage compressor. Okay.
Sir,
Yeah.
means for perfect case of perfect intercooling, we are means compressor is going to work between only two temperatures.
Two temperatures.
Means
Yeah,
can you
yeah,
show
yeah, yeah. It will work between that only. Two.
means can you show that hi
Here,
here sir
here.
means
Yeah. Perfect. For perfect, you can say that T1. No, T1 should be equal to T3, and T2 equals to T4. T2 should be T4. Okay.
means this pattern will keep on repeating.
Yeah, this is will be same as the that of gas turbine we have already discussed. Hello.
Yes, means this pattern will be repeating to left side T4 to T5.
Yeah.
But never happens in the practice.
Hello.
Hello
Yes,
sir.
sir.
Yeah, it is for perfect cooling only. It will repeat keeps on repeating.
Possibility.
But actually, in in the problems, they will never give you perfect intercooling. They will only say that they are using intercooling. If they will give perfect intercooling, then only you have to assume that. Okay.
Okay, means unless and until they use perfect word, we should not consider it.
Yeah. Then if they are saying you have to use intercooler, then in that case we don't have to use that. Okay.
What sir?
In that temperature T1 equals to T3, and this two you have to use for if they are only asking you, that we will discuss in when we are doing the numerical only. Okay, we are moving
Yes sir.
directly to the numerical. From there we will discuss. Okay. हम्म, आ रहा हूँ. So we will do some problems. Okay, so I will write the problem, then we will do. Determine the minimum number of stages required in air compressor in which air enters at a pressure of 1 bar and temperature of 27 degrees Celsius and delivers at 180 bar pressure. The maximum discharge temperature is limited to 150 degrees Celsius. Consider the value of n is equals to 1.25, assuming perfect intercooling between stages. You have to find the value of the n number of stages. Okay. Hello. Have you got the question?
Yes, sir.
I'll write the data. They have given us the initial pressure P1 1 bar. Final pressure they have given. They haven't given the how much stages are there. They have directly given the final pressure 180 bar. Value of n they have given 1.25. Initial temperature they have given 300 Kelvin, and the temperature after 1 bar and delivers maximum temperature is limited to 150. Okay, so they have given T2 because a perfect intercooling they have already mentioned, so T2 will be same. T2 T4 all will be remaining same. So maximum temperature also they have given, that is 150 degrees Celsius. So that you have to convert in Kelvin. 1 plus 273, they have given that 27 degrees Celsius actually. So 423 Kelvin. Okay, has anyone got the answer? Hello.
Three stages.
Hello.
So is there also three stages?
Yeah, it is 3. So okay, we'll do the problem now. We already know that the overall pressure ratio is given by uh, pressure ratio at each stage
To the power n.
to the power n. Okay, so overall pressure ratio is we don't know, we only know the final pressure. upon initial pressure we can write, or you can write P higher upon P initial, and pressure at each stage we don't know. So we are assuming after first it is compressed from 1 to 2. So P2 upon P1 to the power n we can directly write. Okay. So P higher we know, that is 180 final pressure. Initial they have given 1 bar, and P2 upon P1 to the power n. So first we have to determine P2 upon P1. From here we can easily determine. Okay, so for determining P2 upon P1, they have given the initial temperature and the temperature up to which it is compressed, and they have given intercooling, perfect intercooling. So what we can directly write from here is that uh, T2 for polytropic condition, we know that T2 upon suppose 1 to 2 is polytropic. So T2 upon T1 we can write P2 upon P1 to the power n minus 1 upon n. We can directly write from here. So T2 they have given 423 Kelvin, and T1 they have given 300, and P2 upon P1 we don't know. Only P1 we know, and they have given 1.25 minus 1 upon 1.25. So what is the value of P2 upon P1 we will get from here? Can anybody tell?
5.5.
Yeah. So we will get P2 upon P1 from here 5.57. So if we will put this value in that equation 1, this one, this is 1, this is 2. So put 2 in 1. So what we will get? 180 upon 1 is equals to 5.57 to the power n. Suppose we will take a log on both sides. So log 180 into n log 5.57. So from here you will get approximately equals to 3. You will get somewhere around 2 point. So it will come 3. Okay. Hello.
Sir,
Yeah.
but it is giving 3.0227. So it indicates that if we are going to use three stages, then at the end we will not get 180 bar.
What again?
But
Can
but it is close to 180. 172 bar is approximately.
Means I was saying that this n is approximately coming
yeah, it will
3.0227,
you
sir.
because you cannot write stages in points now. That's why you have to take the nearest integer.
But by doing that, this
It
in
will, yeah,
our out,
output will reduce or increase, but it will come close to 180 bar, na?
yes, yes.
Yeah. Okay.
Sir, how to approach this problem without perfect intercooling?
Without perfect intercooling, uh, uh, without perfect intercooling, I think they will not ask. They have asked, if they will ask, then they will ask with perfect intercooling. If they will not ask, then I think the temperature, if perfect intercooling is not mentioned, if perfect intercooling is not given, they have only mentioned that if the intercooling is given. So previously what we were doing, that for perfect intercooling we were assuming that 1 2 3 4. Okay, so T1 is equals to T3, we were assuming T2 is equals to T4. So if they will give us that perfect intercooling is not given, then the temperature at each and every time will be different. Suppose it may be higher here, then it will decrease further, then it will be higher, like this. 1 2 3 4, all the temperature will be different. Okay, then the problem will become more complicated, uh, and this type of problem they will mostly ask in conventional type of, because if they will give that only a perfect intercooling is not given, then it will consume a lot of your time in the problem. So I don't think they will give this type of problem. They generally give in engineering services exams, where you are having time to solve the conventional type of problem. You can find each and every temperature and then solve. Okay,
Okay, sir.
so we'll do another problem. Single stage compressor is given. Okay, a single stage compressor is given with bore dia is equals to 200 millimeter and stroke is equals to 300 millimeter. Okay, and it runs at a speed of 500 rpm. Okay, so the clearance clearance volume c uh, vc they have given 5% of swept stroke volume or swept volume. Okay, and the value of n they have given 1.3. If the intake pressure that is p1 they have given 97 kilopascal and temperature T1 20 degrees Celsius, and the discharge pressure that is P2 they have given 550 kilopascal. Okay, uh, then we have to determine for this condition volumetric efficiency first, second is the power delivered. That is they have given D, this is the L.
Sir,
Yeah,
is it volumetric efficiency point means 86?
yeah, 86. It is right. It is 86%. Yeah. Can you determine that power? Please calculate. I'm coming just within 2 or 3.
सूरज कितना आ रहा है पावर डिलीवर?
नहीं आया अब तक।
ठीक।
Hello. Hello.
हाँ हाँ
Yeah, has anyone got the answer?
सर 1.6 किलोवाट करके कुछ आ रहा है।
No. Okay, we'll calculate. Volumetric efficiency, you already know. Solution eta v 1 plus c minus c to the power p higher upon p lower to the power 1 upon n. It is given by this, and you have already been given that vc equal to 5% of the vs, and c we already know it is given by vc upon vs. So if we will it is given by this, so vc upon vs will come out as 5%. Okay, which we can write it as vc upon vs is equals to 5 upon 100. We will remove that percent. Okay, so already it is given that p higher pressure, that is p2, they have given single stage compressor, so 550 kilopascal it is given. P lower they have given 97 kilopascal, so directly put this value in this formula, and also they have given 1.3. So eta v we will get 1 plus 0.05 minus 0.005, 550 divided by 97 to the power 1 upon 1.3. So when you will solve, we will get 0.86 or 86%. Okay,
सर इज पावर डिलीवर 13.3।
yeah, it is closer 13 point, it is somewhat 13.
ओके सर।
So from here we have already got eta v. Now we know that eta v is given by actual volume upon total swept volume. Okay, so eta v it is given 0.86, so we actually we have to find out, divided by that swept volume we have to find out. So v swept we already know that it is given by pi by 4 bore area, that is area of the bore into stroke length into n. Okay, so this is the uh, swept volume formula. So we swept from we have been given all the values, pi by 4, the bore diameter they have given 200, so we will directly write in terms of meter. 0.2 square into stroke length they have given 300 millimeter, so zero point 0.3, and they have given 500. So what is the swept volume we are getting? Hello.
9.42. 9.42, sir.
9.42 millimeter cube
Four.
per minute. Okay, now this we will put in this formula here. So 0.86 is equals to v actual divided by 9.42. So we actually will get directly 0.86 into 9.42. So what we are getting here? Hello. Hello.
2 है या 4.71 है?
What are you getting here? Swept volume, what you have got?
4.7।
4.71. Okay. 4.71. And this actual volume? It will be 4 point something. What it is?
0.05।
4.05 millimeter cube per minute. Now we already know that mm, uh, work input Actually, we have here we can, okay, no problem actually. Work input is equals to n into n minus 1 into p1 v actual upon p2 upon p1 to the power n minus 1 upon n minus 1, and they have given 1.3, 1.3 minus 1, p1 they have given 97, v actual 4.05. Since it is given in minutes, so we can convert it into seconds by divided by 60, and p2 they have given 550 upon 97, 1.3 minus 1 upon 1.3 minus 1. So from here we will get 13.98 kilowatt. Please check. You will get somewhat here on 13 point something you will get. What were you getting? One guy was getting 13 point.
3 आ रहा था सर.
Yeah, then you can write 13.33. It is somewhat closer. They will give you a range 13 to 14. They will give. You can any answer between that they will accept. Okay. Hello.
Yes, sir.
Is it fine?
Yes, sir.
Okay. We'll do one more problem. Two-stage compressor with perfect intercooling delivers 5 kg per minute of air at 16 bar pressure with intake conditions of 1 bar pressure, 300 Kelvin, and value of n is 1.3. Then we have to calculate first power delivered, total power. Okay. Second, heat transfer, heat transfer in intercooler. Okay. Third one is isothermal efficiency. And I will tell you what is isothermal efficiency. Isothermal efficiency is ratio of the isothermal work done to the actual work done. Okay. Can you calculate?
Sir, is it actual by isothermal?
No, isothermal by actual. Isothermal, you already know P1, V1, that formula. From there you can calculate isothermal work done. And actually you will already work calculate from power delivered.
Yes.
I have given enough of the hints. Hello. Hello.
Sir, power is it 27.86 kilowatt?
No, it is somewhat closer. You're closer, but it is not correct. Will come somewhere around 23 to 24 kilowatts in between. Okay, so we'll do now this problem. So, given data, what it is given, it is a two-stage compressor. Okay, so initial condition m dot they have given that 5 kg per minute. P1 they have given 1
Yes, sir.
bar.
23.44 kilowatt.
Yeah, it is correct. T1 300 Kelvin, and they have given 1.3, and final pressure they have given 16 bar. Okay, so uh, uh, we uh, we know that since they have mentioned perfect intercooling, so for perfect intercooling we know that total work done is equals to n into work done in each stage. Okay, so if we can determine the work done in one stage, then we can easily determine the uh, that total work done. So we know that for perfect intercooling, the overall pressure ratio, is equals to pressure ratio in each stage to the power n. Okay, so overall pressure it is given 16 p higher, and lower pressure is 1. Okay, and intermediate pressure that p2 upon p1 we can write, and number of stages is 2. So p2 upon p1, what we will get 4. Okay, and p1 already they have given 1 bar, so p2 we will get 4 bar. Okay, from here now you will put this. Now work done in first stage. Okay, so we can determine n into n minus 1 into p1 v actual bracket p2 upon p1 to the power n minus 1 upon n minus 1 is equals to everything they have given, n into n minus 1, p1 v1 we can write m dot rt1 p2 upon p1 n into n minus 1 upon n. So n they have, what is the value of n? 1.3, 1.3 minus 1 into m5, they have given kg per minute, so we will convert into kg per second. R they have given nothing is mentioned, just take 0.287. For air they have mentioned uh, temperature 300 Kelvin, and P2 4 upon 1 to the power 1.3 minus 1 upon 1.3 minus 1. So what you have got for the first stage?
23.44, sir.
No, this is for the first stage total, not I am asking. For the first stage what you are getting?
11.72.
11.72 kilowatt.
Sir, is the answer to second is 9.47 kilowatt?
9 point yeah, it is closer, 9.5 kilowatt. It is almost correct. So total work done, it will be equals to 2 number, there are 2 n into single stage. So you from here you will get 23.44 kilowatt. Okay, total work input or power you can say that, because it is already in watt, so you can call it as power also. So second is they have asked work done in heat transfer in intercooler. Okay, so intercooler on TS diagram, TS 1, 2, 3, 4. So 2 to 3 process is intercooler. Okay, so Q 2 to 3, how we can write? Because we are dealing with air, so m dot Cp into T2 minus T3, because T2 is the higher temperature. Okay, m dot they have already given 5 divided by 60, we will get in kilojoule per second from here. Cp for air, it is 1.005. T2 temperature we don't know, and since perfect intercooling is given, so T1 is equals to T3, that is 300 Kelvin, so minus 300. Okay, so T2 we can directly calculate, because 1 to 2 is a polytropic process. For a polytropic process, P2 upon T2 upon T1 is equals to P2 upon P1 to the power n minus 1 upon n. And T2 we don't know, T1 is 300, that is P2 is 4, 1, 1.3 minus 1 upon 1.3. What is the value of T2 you will get? Hello,
13.1 Kelvin.
413.1 Kelvin. Okay, so this you will put there. From Q to 3 heat transfer you will get 5 divided by 60 into 1.005, 413.1 minus 300. So what you will get Q2 from here? 9 point, somewhere around 9.5 kilowatt you will get.
Yes, sir.
Okay, now third they have also isothermal efficiency. Okay, so isothermal efficiency is given by isothermal isothermal upon work actual. So work actual we have already calculated. What is the work actual? That is 23.44 kilowatt. Okay, now isothermal work we will calculate. It is, we know that isothermal process P1 V1 log V2 upon V1. For isothermal process, work done is given by this. Okay, is it fine? Now from here we can write P1 V1 T1 into log, the volume are not given. So for isothermal process, uh, since temperature is constant, so we can write P1 upon P1 V1 is equals to P2 V2. So V2 upon V1 we will get P1 upon P2. Okay, so with this we will put here, and so work isothermal we will get m dot RT1 log
Sir, in
P1.
isothermal also consider two staging.
No, no, no. In isothermal we take initial conditions only, na?
Sir, to two staging will be considered or not? Like P1 by P2 will be 4, 1 by 4, or
Yeah,
like 6.
here also you have to consider two stages only. Here we will consider
Okay,
for the first and then multiply it by 2. You will get the two work done for that total two stages. Okay.
okay, sir.
So what you are getting from here, work isothermal. What you will get 5 by 60 into 0.287 into 300. Okay. So log P1 is 1 upon 4. What you are getting? This, can you calculate?
9.946.
9.94946. Okay, so total isothermal work done will be equal to 2 into 9.946. What you are getting here? 19 point something. What can you tell?
19.89.
Okay, 19.89 kilowatt. Okay, so isothermal efficiency will be work isothermal upon work actual. So 19.89 divided by 23.44. So what you will get? Can you calculate?
84.87%.
84.87%. Okay, this is the answer. We'll do one more problem. In a three-stage compressor, okay, initial pressure, inlet pressure is P1, discharge pressure is P4, the intermediate pressures are P2 and P3, where P2 is less than P3. The total pressure ratio of the compressor is 10, and you have to assume that pressure ratio at each stage is equal. Okay, so if P1 is 100 kilopascal, then you have to find P3 in kilopascal. Can you do it?
$464.
Yeah, it is right, 464. We'll do this.
Sir,
Yeah,
here we are assuming RP at each stage is equal, means
yeah.
we are assuming it as perfect intercooling.
Yeah, if they will not give directly that you have to assume a perfect intercooling, then they will give. They can also give you a statement like this, that you have to assume that pressure ratio at each stage is equal. That indirectly means that the intercooler is working. Compressor is working on a perfect intercooling. Okay.
Okay, sir.
Yeah. So they have what they have given, overall pressure ratio. Overall pressure ratio is equals to pressure ratio at each stage to the power n. Okay, so initial pressure they have given, what they have given. So there are three stages are given. Okay, that it will draw. That is on PV diagram. 1 2 3 4 5 6. First stage second stage, and this is third stage. Okay. So P2 upon P1 is equals to P4 upon P3 is equal to P6 upon P5. Okay. So overall pressure ratio they have given 10, and each stage is equals to, we can write P2 upon P1 to the power 3. Okay. So P2, or you can directly write it like as RP, pressure ratio. So here you can directly write RP to the power 3. So RP to the power 3 is equals to 10. So from here RP, what you will get? RP is equals to 10 to the power 1 by 3. What is the value of RP? Hello. Hello.
Yes, sir.
What is the pressure ratio you are getting? Hello.
2.1,
2 point
2.15, sir.
2.15. Okay. So now, since all the pressures are same, so P2 upon P1 is equals to 2.15. So P2 we don't know, P1 we know. They have given, what they have given, P1 pressure 100. So 100 to the power 2.15. So what you will get? 2.15 into 100. What is the value you are getting for P2? 215 kilopascal. Okay. Now again they have given that P4 upon P3 is also RP is same. So it is 2.15. So P2 upon, wait, wait. Uh, for each stage they have given same, na? So we can write after two stages. How we can write? Pressure ratio, after two stages. Okay. So pressure ratio after two stages can be write like as pressure ratio at each stage to the power, mm, directly we can write from P2 and P3 what they have asked actually, pressure P3 na.
Is it 464.15 kp?
Yeah, it is correct. I think RP you have calculated wrong, someone.
No, sir. I am also getting 2.15.
2.15 into 100 P2. Wait, pressure ratio after two stages, that is P2 into that is correct, and pressure 2 and 3 are same. So I think it should come 215 because 2 and 3 are at same pressure. Here you can see, because intercooler on TS diagram 1, 2, 3, 2 and 3 are at same pressure. So pressure should come 215 only.
No, sir. It is after only first stage.
We want P4.
No, I have already asked, we have to find P3.
Okay, sir.
Okay. So P2 and P3 are same. So you can check. So P2 is equals to P3 is equals to 215 kilopascal. Okay.
Sir, they have given three stages between 1 to 4.
Yeah,
Means 1 to 2 and 2 to 3. Two
yeah,
stages.
yeah. The three stages they have given. First one is 1 to 2, then second stage is from 3 to 4, and then third stage is from 5 to 6. But the pressure for 2 and 3 are same, 4 and 5 are same because it is a intercooler is installed here. Here it is a intercooler. Here it is a intercooler. Okay.
Sir, this diagram is given or not?
No, they will not give this diagram. You have to assume by yourself, and this diagram also you can take. 1, 2, 3, 4, 5, 6. This is the intermediate pressure. This is equal. This also is equal. Okay. On a TS diagram, you can represent it as like that. Is it fine? Hello. Okay. One more last
Yes, sir.
question. One more last question we'll do. Then we'll finish this power plant engineering. Okay. So a single wait a two stage compressor with perfect intercooling delivers air at 16 bar. Assume intake state at 1 bar and 15 degrees Celsius. The pressure ratio at each stage is options 2, 3, 4, 16, 8, 4, 2. It is a direct problem.
Four.
Yeah, 4 is the correct answer. Directly you know that overall pressure ratio is equals to pressure ratio at each stage to the power n. So 16 upon 1 P2 upon, or directly write RP to the power 2. So 16 to the power half is equals to RP. So 4. Okay. Hello.
Yes, sir.
Yes, sir.
Okay. That's all from, I think they will ask, they cannot ask more than that because they haven't asked most question on this compressor part, because most of the topic for compressor are already covered in that gas turbine and thermodynamics. So not much is left in this single-handedly topic. Okay. So they will ask question like this only if they want to ask in compressors. So so this will be the end of our class, because the last date given by the NPTEL is 31st, and 31st is, I think, what is on 31st? 31st is on Saturday. Okay, and 31st is the last class. So we will not have any other lectures from the next week. Okay. So, how was your experience?
Mm.
Did you learn something or not?
Yes, sir. Definitely, sir.
Yes, sir.
Because I am also taking the classes for the first time, so I I, I can improve uh, in the next time if I will take the classes because
Yes, sir. From phase 3.
yeah, if I will take in phase three, then I can improve from there.
Mhm.
So okay,
Sir,
so when is your gate exam? Yeah,
February 4th.
yeah, four
Mm.
fourth Feb.
Yes, sir.
Okay, okay, okay. So best of luck for your gate exam.
Many thanks, sir. Many
Yes,
thanks.
sir.
Okay, do well.
Yes, sir. Definitely, sir.
Okay,
We'll try. Thank you for
okay,
supporting us.
okay, okay. Thank you.
Yes, sir.
Okay, okay.
Sir,
Best
Thank you.
book.
many of the faculties are teaching in the broad
Yeah,
syllabus wise. You are taking like specific gate syllabus only.
yeah.
That is,
Because you don't need that much depth for gate. You just need to uh, learn the concepts. They ask
uh,
conceptual questions only. They don't ask elaborative type of question because they also know that you are only having 3 hours. So if you know the concept, then you will be able to solve the problem more in a easy way in the gate exam.
yes,
But
sir.
please keep in mind the units while solving the problems in the gate because I was facing the same. I lost around 5 to 6 marks. I got 73 or 74 marks in gate 2000, 2019. So uh, I lost many marks because of that units. So please be uh, while solving the problem, please look at the units properly because uh, suppose you are if you are not looking to the units and you have solved the problem, the wrong answer also might be there in the options, one of the four options, especially in MCQ types problem where they have given four options. All the four options out of that only one will be correct, but they already know that from all different ways you can get the wrong answer. They will put that option also in that. So please keep in mind while solving the numericals that unit part because uh, that can significantly improve your rank. Hello.
Yes, sir.
Okay, okay.
Yes, sir.
Sir, we covered the all syllabus,
Yeah,
but
we have
mm,
we have done all the syllabus, which is very important for the gate. We have covered all the topics, so don't worry about it. That okay?
sir, sir, where to practice the
Just practice.
questions?
Yeah, just
We
practice and practice. Just now give the test series if you have taken some test series. So just give the test series as many exams as possible because it will increase improve your speed and accuracy.
yes, sir. We learn the all subjects, but
Now,
more practice is required
yeah,
at the time.
now just revise and just give the exams. The more exams you will give test series, the more confident you will be on the examination day. Because in the end all the students who are appearing for the gate exams who have prepared, they know the concept, but the problem comes while solving the problems that uh, uh, can I speak in Hindi if you can understand?
Yes, sir. Yes, sir.
Yeah.
No, sir.
The- Okay, then I'll speak. The problem comes is that you are suppose you are stuck in one problem, then you waste a lot of 5 or 10 minutes in one problem. So and the suppose that they might have put that problem for that purpose only there in the initial phases, so that you put most of your time on that problem. You have to understand it, that gate is not an that selection process. It is basically a rejection process. Gate is a rejection process exam. So they will put the problem. Suppose if you will stuck in one problem, you will waste a lot of time in that problem, and you will not be able to view all the questions till the end. And who knows that in the end they might they have put easy questions. Those you can solve in 1 or 2 minutes only. So first process you should do in the gate exam is that first you should do the problems which by the site only you can see that I can do it directly. So first try to go through to the whole paper and solve as many as problem you can. So suppose there are 65 problems. Out of that 10 are that mm, you can say that 10 are those problems, general studies. So remaining 55 are for mechanical engineering. Out of that 55, around 30 to 35 questions are easy that you can directly attempt. And remaining 15 problems, 5 to 10 problems are medium, and 5 to 10 are tough. So you try to solve that 45 problems, uh, and at the end, if you get time, then solve that 5 to 10 problems, which are very tough, that can consume your time. So first you should try to go through the whole paper once in 1 or 1.5 hours. In that you can solve all the easy problems. After that you can give half an hour or 45 minutes to the medium problems, and then remaining 45 minutes for the tough problems you can give. Out of the tough problems, if you are able to solve 5 or 6 also na, you will get a very good rank.
Sir, please repeat it again, sir. Please, kindly.
देखो, मैं ये बोल रहा था कि
For
गेट गेट का ये पेपर जो रहता है ना, वो उसमें क्या है, पूरा एक बार पहले पेपर देख लो। उसमें क्या रहता है कि कई बार वो लोग टफ क्वेश्चंस पहले डाल देते हैं, तो उसमें तुम्हारा बहुत ज्यादा टाइम निकल जाएगा।
हाँ सर।
तो उसको काउंटर करने के लिए मैं तुम्हें बोलूंगा कि पहले तुम इजी प्रॉब्लम जितने भी हैं सारे सॉल्व कर लो। फिर एंड में क्या कहते हैं, तो जो 55 मैकेनिकल इंजीनियरिंग के प्रॉब्लम आएंगे, उसमें से 30 to 35 प्रॉब्लम्स तुमको इजी रहेंगे, जो तुम देखते ही सॉल्व कर
यस
लोगे।
सर।
उसके बाद फिर 5 से 10 प्रॉब्लम मीडियम स्टेज के रहेंगे, या 15 प्रॉब्लम बोल सकते हो मीडियम के रहेंगे, जो कि थोड़ा तुमको सोचना पड़ेगा। और बाकी 5 से 10 बहुत टफ, थोड़ा टफ डाले जाते हैं, ताकि उससे ही रैंक डिसाइड हो। तो वो आखिरी के 5 से 10 वो तुमको डिसाइड करने हैं कि वो तुमको कौन से लग रहे हैं, जिनको तुम एंड में कर सको, जो टाइम तुम्हारा खा रहे हैं। तो अगर तुमने 45 जल्दी कर लिए और आखिरी में तुम्हारा आधा घंटा
हाँ।
कुछ बचा है, तो उन 5-10 प्रॉब्लम से 5-6 भी तुमने कर लिए, तो तुम्हारा रैंक बहुत अच्छा आ जाएगा।
ओके सर।
ओके, ओके देन, ओके, बेस्ट ऑफ लक फॉर योर गेट एग्जाम।
Thank you, sir.
ओके,
Sir, are you from which IIT?
आई एम फ्रॉम IIT Madras.
Okay.
ओके,
Okay. Thank you, sir.
ओके, थैंक यू। या अभिजीत,
Sir, what is your stream, sir?
आई एम मैकेनिकल इंजीनियरिंग ओनली। आई एम इन मैन्युफैक्चरिंग।
No. Manufacturing.
या
Yes. I mean specialization, sir.
या स्पेशलाइजेशन मैन्युफैक्चरिंग। ओके,
would it be your मतलब सर ये आपका लास्ट ईयर या और 2-3 साल है
नहीं यार,
आप एमटेक
नहीं मेरा अभी मेरा क्या कहते हैं सेकेंड ईयर चल रहा है।
पीएचडी का सेकेंड ईयर सर
या
ओके सर थैंक यू सर
ओके थैंक यू। Okay, thank you and best of luck for your GATE exam.
थैंक यू
Thank you, sir.
Okay, thank you. Okay, bye. Good night.
सर